Hello everyone, and this is Sandeep. You are watching Samyan's Academy, and in this session we are going to discuss about magnetic effect of electric current. Let us start. So in this chapter we are going to discuss about Ncert experiment, properties and characteristics of the magnetic field lines, magnetic field due to current carrying conductor, right hand thumb rule. Let us start. In this chapter we will study the effect of electric current. Moving charges or electric current generates a magnetic field. Okay, moving charges or electric current generates a magnetic field. This was proved by Hans Christian Ørsted, and he showed that there is a relationship between the electricity and magnetism. And also this his research later used in radio, television, etc. The unit of magnetic field strength is named Ørsted in his honor. Right, now you see, let us see the experiment of the Ørsted. When you take the bar magnet nearer to it, it will get deflect. Now you see, when you take the bar magnet nearer to it, the magnetic needle get deflect. Yes, observe the deflection in the magnetic needle. When you take the bar magnet nearer to it, now it is deflecting. Right, now it is so when you take the cell and when you connect the positive terminal, negative terminal to this conducting wire, then current flows from this conducting wire towards upward direction. Now you observe the deflection in the compass needle. It deflected towards in west direction. Okay, now it is deflecting in west direction. When there is no current in the battery or cell, the magnetic needle comes at rest. Now you see, when there is no current in the conducting wire, the magnetic needle comes at rest. When you change the direction of the current by changing the polarity of the cell, now you see, now current is moving downward direction. The deflection in the magnetic field, now it is east direction. Okay, so in this way we can confirm that when there is a current around the conducting wire, it will develop the magnetic field. Due to that magnetic field, the compass needle get deflect. Right, now you see the next one, Ørsted experiment that on passing the current through the copper wire XY in this circuit, the compass needle which is placed near the conductor which get deflected. So if you reverse the direction of the current, the compass needle deflect in reverse direction. Okay, suppose if we stop the current, if we stop the direction, if we stop the flow of current, the needle comes at rest. Hence it can be concluded that there is a relationship between the electricity and magnetism are linked to each other. It shows that whenever the current will flow through the conductor, then a magnetic field develop. Okay, on passing the electric current through this XY conductor, the compass needle which is placed near to this conductor get deflected. Right, when it is moving upward direction, so it deflected towards the west. When it is moving the current, when the current is moving in the downward direction, it will get deflected in the east direction. So from this experiment we confirm that whenever there is a current in the loop, or whenever there is a current in the conducting wire, there is a magnetic field. That means here current and magnetic field are linked to each other. Right, now this is about Ørsted experiment. Is it clear? Now move on to the next one. Then how do you define the magnetic field? It is a region surrounding a magnet in which force of magnet can be detected, and also it is vector quantity having both direction and magnitude. Now you see, you take the bar magnet. Okay, so when you sprinkle the iron filings around it, so it will take the alignment of like this, right? And this is the region around the magnet where we can feel the force of this magnet. When you take the iron nail nearer to this region, and it will get attract towards this bar magnet. Okay, the region around the bar magnet, or the region around the magnet where we can feel the, or where we can experience the force of attraction of the magnet, and that region we called as magnetic field. Is it clear? So what is the magnetic field? It is a region surrounding a magnet where the force of magnetic can be detected. It is a vector quantity having both direction and magnitude. Now this is a compass needle. Just now we have seen, it is a small bar magnet whose north end is pointing towards north pole and south end is pointing towards south pole of the earth. This north end direction, it is showing the north pole, and the south end direction, it shows the south pole. Okay, now magnetic field lines. Okay, before going to this, what is the magnetic field lines? Then how that magnetic field lines we can understand. Let us take one bar magnet here. Now you sprinkle the iron filings around the bar magnet. Now we can see this iron filings take the alignment of iron fillings takes some alignment pattern, right? So if iron filings sprinkle near the bar magnet, the lines along which the iron filings align themselves, and these lines represents the magnetic field lines. Have you observed this? And this is about the magnetic field lines pattern. Okay, then we can conclude that hence magnetic field line is a path along which a hypothetical free north pole tend to move towards the south pole. Now these are the pattern we can observe around the magnet when you sprinkle the iron filings. All iron filings align themselves in some pattern. This pattern represent the magnetic field lines. And this is a hypothetical line, we can assume that. So the free north pole tend to move towards the south pole, right? Have you observed this magnetic field lines? These magnetic field lines are originate from the north and terminate towards the south pole, right? Inside the magnet, how it will move? Inside the magnet, it will move from the south pole to north pole. Now you see, inside the magnet it will move from the south pole to north pole, and outside of the bar magnet it moves from the north pole to south pole. Hence it will form a continuous closed curved loop. In this way we can see the magnetic field lines. These are the magnetic field lines. And now you observe where the magnetic field lines are very closer to each other, at the pole. Now you see, in this region the magnetic field lines are very close to each other, right? Here also we can see magnetic field lines are very close to each other. So that will indicates if magnetic field lines are very close to each other, where we can experience more magnetic field strength, means at the poles the strength of the magnetic field is more. Now you see, in this region the magnetic field lines are very far from each other, right? So here the magnetic field lines are very far from each other. That indicates that if magnetic field lines are very far, means here we can see the less magnetic field, okay? And in this region we can feel the less magnetic field. Where we can feel the more magnetic field? At the poles. And also you observe this, and in this experiment also, now you see where we can see the magnetic field lines more. Now you see here at the poles, here we can feel the more magnetic field strength, right? Have the characteristics of the magnetic field lines. The direction of magnetic field lines outside the magnet is always from north pole to south pole of the bar magnet and are indicated by an arrow. Now you see, all field lines are originated from the north pole, okay? And it will move towards to the south pole, so which is indicated with one arrow mark direction. So that direction indicates that the field lines are moves from north pole to south pole. Now you see, inside the magnet it will move from the south to north, like that it will, so it will form the continuous closed curved loop. Now see, outside the bar magnet, the direction of field lines from north pole to south pole. Then inside the magnet, it will move from the south to north. Like that, it will form a continuous closed curved loop like this. Okay. Outside the bar magnet, the magnetic field lines move from the north pole to south pole. Inside the magnet, the magnetic field lines move from the south to north. Like that, it will form a continuous closed curved loop, right? And how do you decide the strength of the magnetic field lines? Yes, closer the lines, more will be the strength, and farther the lines, less will be the magnetic field strength. Okay, you if you observe the at the poles, here the field lines are very close to each other, right? At the pole we can see the field lines are very close to each other, okay, where that strength of the magnetic field is more. Here the field lines are very far to each other, here magnetic field strength is less, okay? And now you see, any two magnetic field lines never intersect each other. So if they intersect each other at the point of intersection, it has to show two direction, okay? At one point magnetic field line never shows the two direction, so it is impossible. Now you see, these are the two magnetic field lines. So, okay, if these field lines are intersect each other, if two magnetic field lines are intersect like this, let us assume this is the two magnetic field lines. Okay, when you draw the point of, yeah, at the point of intersection, when you draw the two tangents, it will show this direction at the point of intersection. Another tangent when you draw for this line, below line, it will show this direction, right? Now at one point it is showing the two direction. Is it possible? Now we can get confused, right? So it is not showing the particular direction. So one point is showing towards this side, another point showing towards downward direction. So it is not showing the one direction. So from this we can confirm that never the field lines, the two field lines never intersect each other. So if they intersect each other at the point of intersection, it has to show two direction. Okay, magnetic field lines shows only one direction, not two directions, so it is not possible. So from this we can confirm that no two magnetic field lines intersect each other. Okay, then a point of intersection compass needle will show two direction of magnetic field, so which is not possible, right? Move on to the next one. Magnetic field due to current carrying conductor. Let us see now two activities. Let us observe these two activities. So in the first activity, we have taken one bunch of copper wire and we inserted from one cardboard, right? Now you see we are sprinkling the iron fillings around it. Okay. Now when current is passed through this conductor, now we can see the pattern of the iron fillings. Now you see when you tap this, iron fillings align themselves in the concentric circles like this. Here we can see that all iron fillings align themselves in concentric circles. Current is moving in the upward direction, then all iron fillings takes the alignment in the concentric circles, right? This is a first activity we have completed. Let us see one more activity. Here we have placed all compass nearer the conducting wire. When the current is passed through this conducting wire, all compass needle gets deflected. Where we can observe the more deflection? Here. The compass which is very nearer to this conductor, in this we can observe the more deflection. The compass which is nearer to this current carrying conductor, so in this we observe the more deflection. Okay, where we can observe the less deflection? The compass which is away to this conducting wire, so here we can observe the less deflection. So from this we can confirm that okay, the magnetic field lines very nearer to this conducting wire, the field strength is more, right? When you move away to the conducting wire, the field strength is less here. The field strength is going to be reduced when you increase the distance from the conducting wire. This is the second activity. So let us see one more activity. Already we discussed in the Ncert experiment. When you reverse the direction of the current, what will happen? Now you observe the another activity. Let us see now. Now what we have done here, so we have placed the two batteries here. Okay, we are observing the deflection in the compass needle. Means suppose when you are passing the more current, then what is the deflection in the compass needle? When you pass the less current in the conductor, what is the deflection in the compass needle? Now we are going to perform this activity to show the when you increase the amount of current, what will happen? When you decrease the amount of current, what will happen? Let us see. By doing this activity, we can conclude that. So what is the relationship between the amount of current and deflection? Now you see here. Now you see when you place the two cells here, the deflection we can observe here at 54 degrees, right? The magnetic needle deflect towards east direction in 54 degrees. Okay. Now we are changing these cells. Now we are increase the cells up to 4. Now you see the observation. When the current is passed through this conductor, when you place the 4 cells, means you are increasing the amount of current now. Okay. Now you see when you connect this, the current is passed through this copper wire. Now you observe the deflection in the compass needle. Now you observe the deflection in the compass needle. Yes. Now we can observe the deflection is more here now. Deflection now it is showing the 62 degrees. Previously when you take the two cells, the deflection in the compass needle we observed at 54 degrees. When you increase the current by increasing the number of cells, now we can confirm that by increasing the cells, what will happen? The deflection in the compass needle also increases. Okay, previously it was deflected to 52 degrees. Now when you increase the current, it was deflected to 64 degrees, right? 64 or 62 degrees, right? Now here we are doing the one more activity. When you take the compass needle nearer to it, we can observe the more deflection. When you take this compass away to the conducting wire, we can observe the less deflection in the compass needle. So from this activity we conclude that whenever there is a more current, we can observe the more deflection in the compass needle. So from this activity we can confirm that the more current will produce a more magnetic field around it. Because of that, the compass needle showing the more deflection, right? When compass needle, when it is show the less deflection, when there is a less current. Okay, when the current is flowing towards the conductor, it is a less amount. That means the around this conductor we can observe the less magnetic field. So due to that less magnetic field, the compass needle gets less deflection. If it is a more current, it will get more deflection. If it is less current, it will get less deflection. Okay, and one more activity we have done, right? When compass needle is takes away to the current carrying conductor, we can observe the less deflection in the compass needle. When you take it nearer to the current carrying conductor, the compass needle shows more deflection. Okay, when you take the nearer to the conductor, so what will happen? Now you see, again you watch here. Now you watch, when you place this compass needle, when you take away, so the deflection is decreasing. When you move to this conducting wire, the deflection is increasing. Okay, the deflection increasing. So now slightly the deflection is decreasing, right? The angle of deflection is decreases when you take it away to the current carrying conductor. Now when you come to nearer to this, the deflection showing more here, right? So from this activity we confirm that the magnetic field strength is more at current carrying conductor. When you move away from the current carrying conductor, the magnetic field strength is decreases. Okay, now here one more activity we have here. So based on the direction, when you change the direction of the current, the deflection in the magnetic needle also get reversed. Already we have seen in the Ncert experiment. Now you see one more time here. Now the current is moving positive terminal to negative terminal, so the compass needle now deflected towards the east. When you change the polarity, now it is deflected towards the west. Okay, right? Direction of deflection of compass needle reverses when current flows in the opposite direction, right? Means from these activities we can confirm that when current is flowing upward direction in the current carrying conductor, where we can see the magnetic field lines around it. Okay, how they form? In concentric circles. All magnetic field lines are formed in the concentric circles, right? And next activity we have seen that when you increase the amount of current, we can observe the deflection in the compass needle also increases. Means the more current produces more magnetic field, the less current produces less magnetic field around the current carrying conductor. Okay, and also one more activity also we have done. When you take the compass needle nearer to the current carrying conductor, it will show the more deflection. When you move away to this current carrying conductor, it will show the less deflection. Okay, that means where we can observe the more magnetic field strength at the current carrying conductor, nearer to the current carrying conductor. When you move away to the current carrying conductor, then what will happen? The magnetic field is showing the less deflection. Okay, that means there is a less magnetic field. Okay, so when you summarize all these points here, so we can conclude that the above electric circuit in which a copper wire is placed parallel to compass needle shows the deflection in the needle gets reversed when the direction of the current reverse. Whenever the direction of the current reverse, the compass needle also showing the reverse direction deflection, and the compass needle also get deflected in the reverse direction. Right? Now if current is increased, deflection also increase. It shows that current is directly proportional to magnetic field at given point. Now here current is directly proportional to magnetic field. Means here magnetic field indicated with the letter B. Okay, the magnetic field strength is increases when there is a increase in the current. Means B is directly proportional to I. right? So one more point we have here. Now place the compass at farther point from the conducting wire. We see that the deflection in the needle decreases. Means when you increase the distance from the conducting wire, where we can see the less magnetic field. Means with the increasing in the distance, the magnetic field strength is decreases. Means the magnetic field strength is inversely proportional to distance from the wire. B is inversely proportional to 1 by D. Okay. We see the deflection in the needle decreases, thus the magnetic field strength is inversely proportional to distance from the wire. Now one more is there here. A current carrying state conductor has magnetic field in the form of the concentric circles around it. Now you see what is the pattern of these magnetic field lines. All field lines around the current carrying conductor, it forms a concentric circles, right? Now, hence electricity and magnetism are related to each other, and this is about magnetic field due to current carrying conductor. So you have to observe here, when you take the state current carrying conductor, around it the magnetic field is developed in the concentric circles, right? When you increase in the current, the magnetic field strength also increases. When you move away to the current carrying conductor, where the magnetic field strength decreases, from this we can conclude that the magnetic field strength is directly proportional to current and inversely proportional to distance from the wire. Okay, is it clear everyone? Now move on to the next concept, that is right hand thumb rule. Okay, to know the based on the direction of current, the magnetic field direction also varies. Then how do you know that the direction of the magnetic fields based on the current carrying conductor, based on the direction in the current carrying conductor? Okay, suppose when you take the state current carrying conductor, then hold your right hand. So this is we call as a right hand thumb rule. So just you place the right hand like this, right hand thumb rule. So this thumb indicates the direction of the current. The curling finger indicates the direction of the magnetic field lines. Let us see. When you place the thumb in this direction, this thumb direction shows the direction in the current. Okay, where we are placing the thumb, in the direction of current we are placing, right? So when you fold these fingers gives the direction of field lines. Now it is in the anti-clockwise direction. Means if current is moving in upward direction, the magnetic field around the state current conductor is concentric circles. And what is this magnetic field lines direction here? That is in anti-clockwise direction. Okay, when current is moving in the downward direction, when suppose let us assume this is a current carrying conductor, so when the current is moving in the downward direction, you place the thumb in the reverse direction like this. Okay, now these fingers, the curling fingers indicates the direction of the magnetic field lines. Now you see, when this current is moving downward direction, the finger curls in this direction, means it is in the clockwise direction. Okay, based on this right hand thumb rule, so we can know the direction of magnetic field lines. When current is moving upward direction, there we can see the magnetic field lines are arranged in anti-clockwise direction, right? Whenever the current is moving in the downward direction, where we can see the magnetic field lines are produced in clockwise direction. Okay, so this is a right hand thumb rule. Okay, this is the activity just now we have performed. Kill the iron fillings or iron filings around the concentric circles near the current carrying conductor. Okay, all iron filings takes the alignment in the direction of concentric circles. Okay, when you tap this, we can see the alignment of iron filings. All iron filings takes the alignment in concentric circles. Okay, yeah, like this. When current is moving the upward direction, what is the field line direction here? Anti-clockwise. When current is moving downward direction, what is the direction of the field here? Clockwise direction. Just remember, this is a right hand thumb rule. Then how do you define this? It is a convenient way of finding the direction of magnetic field associated with the current carrying conductor. Hold the state wire carrying current in your right hand such that the thumb points towards the direction of current. Then your folded fingers around the conductor like this. Okay, will show the direction of magnetic field. Okay, the curling finger shows the direction of magnetic field. The thumb shows the direction of the current. Is it clear everyone?